somewhere beneath the ocean, there are coastlines that no one alive has ever walked on, beaches that were busy with human life, river mouths where people camped and fished, shallow plains stretching for hundreds of miles where families built their worlds and then watched the water come. Not in a single catastrophic wave, not overnight, but steadily, relentlessly, over thousands of years, the sea rose and swallowed everything. And because it did, we may be missing a very large piece of the human story. Here's the thing that keeps archaeologists and geologists up at night. When we talk about early human history, about where people lived and how they moved across the world, we're almost entirely working from evidence that survived on land, caves in hillsides, campsites on high ground, burial sites well above the modern waterline, and that makes sense, because that's where the evidence still exists. But for most of human prehistory, some of the most attractive real estate on the planet wasn't up in the hills. It was along the coast. It was on the wide, flat, food-rich plains that fringed the continents before the Ice Age ended and the sea came in. Those places are gone now. Most of them are sitting under anywhere from a few meters to well over 100 meters of ocean water, and they have been for thousands of years. Whatever was left behind down there, the hearths, the middens, the shell heaps, the wooden structures, most of it has been scattered by currents, or buried under sediment, or simply dissolved by time. The absence of evidence isn't evidence of absence. It's just evidence of water. If you're listening to this right now, wherever you are in the world, I'd genuinely love to know. Drop a comment and tell me where you are and what time it is where you are. It's something I always check, and there is something quietly astonishing about knowing that someone in Tokyo is winding down for the night at the same moment someone in Toronto is settling in before sleep. We're all drawn to the same kinds of questions across very different skies. If you want to listen without the ads and without background music, you can follow the show on Spotify. The link to support the work is in the description, and it genuinely helps keep this going. Now picture a map of the world. The one you know, the one with familiar coastlines, the shapes of continents you learned in school. Now imagine draining the oceans. Not all the way, just enough. Drop the sea level by about 120 meters, which is roughly the difference between today's ocean and the ocean at the peak of the last ice age around 20,000 years ago. What you get is a fundamentally different planet. Britain is connected to continental Europe across a vast low-lying plain. Southeast Asia looks less like a scattering of islands and more like a single enormous landmass fringed by shallow water. The Persian Gulf is dry land. A large portion of what is now the seafloor off the coast of India is exposed and habitable. Australia is joined to New Guinea. And across all of these newly revealed territories, there are river valleys, lake beds, wetlands, and coastlines that simply do not exist in the world we live in today. People lived there. Not maybe, not speculatively in some vague and unverifiable sense, but almost certainly based on everything we know about how humans behave and where they tend to settle. Coastal environments are extraordinarily productive. They offer fresh water, shellfish, fish, waterfowl, plant foods, and easy travel routes. For hunter-gatherers and early settled communities alike, the edge where land meets sea is one of the richest places on Earth. And for tens of thousands of years, a great deal of that edge was further out than it is today, sitting on ground that is now submerged. That's the gap we're going to spend this episode trying to understand. This is not a story about lost civilizations in the dramatic pseudo-archaeological sense. There are no claims here about advanced technology hidden beneath the waves or ancient empires wiped out by a single catastrophic flood. The reality is both more ordinary and more profound than that. It's about the simple, well-supported idea that normal people, real communities, people building fires and raising children and moving along the land in search of food and shelter, lived in places that archaeology has never been able to study. because those places don't exist above water anymore. And that gap in the record may be shaping everything we think we know about human prehistory. What we're going to do tonight is travel through some of those drowned landscapes one by one. We'll look at the actual geological evidence for where the shorelines were, what kinds of environments existed there, and what archaeology has managed to recover from the seafloor in the places where researchers have been able to look. We'll be precise about depths and dates where the evidence allows it, and honest about uncertainty where it doesn't, because the ocean has not given much back, but it has given some things. And what it has given us is enough to suggest that the coastline we think of as the edge of the world is not the whole story. It never was. To understand what got drowned and why, you need to understand the mechanism, and it's actually not complicated. It's just ice. During the last glacial maximum, the peak of the most recent ice age around 20,000 years ago, enormous volumes of water that would normally be cycling through the atmosphere and oceans were locked up in continental ice sheets. The Laurentide ice sheet over North America was in places more than 3 kilometers thick. The Scandinavian ice sheet buried most of northern Europe. Ice covered large portions of Siberia, the Andes, and the Himalayas, at scales that are almost impossible to visualize from where we sit now. All of that water had to come from somewhere, and it came from the ocean. The result was a global sea level sitting roughly 120 meters below where it is today. Not 20 meters, not 50 meters, 120 meters lower, in some estimates closer to 130. That's the height of a 40-story building. That's the difference between a familiar coastline and a completely different map of the world. When the ice began to melt, that water went back into the ocean. But here's the detail that matters for this story. It didn't go back smoothly. It didn't rise in a slow, steady, gradual incline like water filling a bathtub at a careful pace. It happened in surges, periods of relatively stable sea level interrupted by sudden rapid pulses of rise, events that geologists call meltwater pulses, when the ice sheets destabilized and discharged enormous volumes of fresh water into the ocean in geologically brief intervals. The best documented of these is Meltwater Pulse 1A, which occurred somewhere around 14,600 years ago. In the span of roughly 500 years, possibly less, global sea level rose by somewhere between 16 and 25 meters. That's not a slow encroachment. That's a coastline moving inland at rates that people living on flat coastal plains would have witnessed within a single lifetime. One generation might grow up with the sea a comfortable distance away. The next might watch it cross the horizon they remembered from childhood. The generation after that might find their grandparents' gathering grounds under several meters of water. Within a few human lifetimes, landscapes that communities had occupied for centuries could become sea floor. There were other pulses too. Meltwater Pulse 1B around 11,500 years ago. Possible smaller events at various points between 20,000 and 7,000 years ago, which is the broad window we're most concerned with tonight. The overall shape of post-glacial sea level rise is not a line. It's a staircase, with relatively flat treads and then sudden rises, and the rises are where the damage to the archaeological record would have been most severe. By around 7,000 years ago, sea level had risen to something close to its modern position, give or take a few meters depending on location, which means that the entire transformation from an Ice Age world to the one we inhabit happened within a span of roughly 13,000 years. In terms of human experience, that's not nothing. That's 500 generations. It's long enough for people to develop traditions, relationships with specific landscapes, place names, stories about where the water came from and where it stopped. But it's short enough that the memory of different coastlines could plausibly have been carried forward in oral tradition, passed down as stories about lands that were once there and are now beneath the sea. What kinds of landscapes got drowned first? This is worth slowing down on, because not all terrain responds to rising water in the same way. The geography of flooding is not uniform. River mouths went first and they went fast. When sea level rises, rivers back up. The zone where a river meets the sea extends inland as the ocean advances up the channel. What had been a river delta with productive wetlands, fresh water mixing with salt, rich in fish and shellfish and water birds, could be inundated within years or decades. The delta of a major river during the last glacial maximum might have been sitting 50 or 100 kilometers further out to sea than its modern mouth. All of that terrain, everything from the river's ancient course out to the old coastline, is now submerged, and river deltas are precisely where people camp. They're where hunter-gatherers linger. They're where the earliest settled communities tend to form, because the combination of fresh water, protein from the water, and flat land for foraging is almost irresistible. Lagoons and shallow bays were similarly vulnerable. Protected water behind barrier islands, tidal flats, mangrove coasts, salt marshes. These are some of the most biologically productive environments on the planet per square metre, and they're also some of the most fragile in the face of sea level change. A lagoon that exists because a barrier bar is sitting just above the waterline disappears quickly once the sea rises enough to overtop that bar. What remains is open water with no memory of what it sheltered. Coastal plains, the broad low-gradient terraces that extended outward from many continental margins during glacial low stands, were the largest category of loss. On passive continental margins, the kind you find along much of the American Atlantic coast, the western coast of Europe, the northern coast of Australia, the slope between the old coastline and the edge of the continental shelf is gentle. A rise of 120 metres across a shallow, gradual shelf can move the shoreline inland by hundreds of kilometres. Enormous territories. Not dramatic mountains or impassable terrain, but the kind of flat, well-watered, resource-rich landscape that human communities tend to prefer. This is where the archaeological bias starts to come into focus. The sites we find and study today, the ones that have given us most of our picture of late Pleistocene and early Holocene human life, are disproportionately located inland or at elevation, in caves on hillsides, on river terraces above the flood plain, on high ground that remained above water throughout the whole period. And there's nothing wrong with that evidence. It's real. It's valuable. But it represents a filtered sample. We're seeing the people who were living in the places that survived, not necessarily the places that were most heavily occupied. Think about it in terms of where you'd actually want to live. If you're a hunter-gatherer community in, say, 18,000 years ago, and you have a choice between a sheltered inland valley with seasonal resources and a broad coastal plain with year-round access to marine protein, fresh water from river mouths, mild temperatures buffered by the ocean, and easy movement along the shore, you take the coast, almost every time. Coastal environments buffer against the harshest seasonal fluctuations. They offer redundancy, multiple food sources that don't all fail at once. They support higher population densities than most inland environments. The coast is prime real estate, and it has been for as long as our species has been on the planet. But the coast moved, and when it moved, whatever people had built and left and buried there moved with it into the water. The timescale matters here. We're talking about the period running from roughly 20,000 years ago, near the peak of the last glacial maximum, through to about 7,000 years ago, when sea level stabilised near its modern position. That's the late Pleistocene running into the early Holocene, the transition out of the Ice Age into the world we recognise. It's exactly the period when human populations were spreading, diversifying, developing more complex technologies, and in some regions beginning to experiment with the first forms of plant and animal management that would eventually become agriculture. This is one of the most consequential stretches of human prehistory, and a significant portion of the landscape where it was playing out is now underwater. The sites that survived on land and gave us our picture of this period. The cave paintings of southwestern Europe, the rich shell middens of the South African coast, the early village sites of the Levant and the Zagros foothills, these aren't the whole story. They're the story that the land preserved. The story the sea kept is still mostly unread. Some of it is gone beyond recovery. Organic materials don't survive well under salt water for thousands of years. Wooden structures, woven baskets, plant foods, animal hides, the kind of material culture that would tell us most directly how people were living, most of that is long gone. But stone tools survive. Hearth features can survive if they're buried under protective sediment before the water arrives. Shell middens built up over generations can be preserved if they're buried quickly enough. Bones survive. Occasionally even preserved landscapes survive. Ancient soil surfaces sealed beneath marine sediment. River channels still visible in the seafloor topography. The ghost shapes of a world that existed before the flood. We know this because in a handful of places researchers have actually looked, and what they've found has started to change the way the question gets asked. Not whether people were living on these drowned coastlines, but how much of their world remains to be found, and how much we've already lost without ever knowing it was there. Archaeology has always been a land-based science by default. We dig where the ground is dry, where we can walk, where we can set up grids and screens and shade tents, and slowly peel back layers of soil with trowels and brushes. The classic image of an excavation is a square in the dirt, not a diver in murky water. That simple practical fact has shaped the story we tell about our past more than most people realize. Coastlines, especially ancient ones, are hard in almost every way that matters to an archaeologist. First, there's the physical violence. Surf zones grind and tear at anything in reach. Wave energy on a shallow shelf can move boulders the size of cars, let alone flakestone tools or the delicate traces of hearths and post holes. Tides, storms, and longshore currents continually rework sediments, cutting into old deposits in one season and burying them meters deep in the next. A site that might have sat quietly on a river terrace for 10,000 years can be chewed apart in a decade when it's dragged into the active coastal zone. Then there's burial. Once sea level climbs over an old shoreline, that terrain doesn't just sit there on the seafloor unchanged. In many places it gets blanketed. Fine silts and clays rain down out of suspension. Sand sheets migrate with storms. In drowned estuaries, the mix of river sediment and marine sediment can quickly stack up into thick packages, tens of meters deep in some basins. If there was a campsite, a shell midden, a small village on that surface, it's now sealed under layers of mud and sand. That can be good for preservation, but it's terrible for visibility. From the surface, all you see is a flat seabed. Modern human activity adds another layer of destruction. Trawl nets dragged across the continental shelf can rip up anything that sticks even slightly out of the sediment. Anchors plough furrows through deposits that have been stable since the early Holocene. Dredging for ports and shipping lanes scoops out channels straight through ancient landscapes. These disturbances don't just move artifacts. They mix them, scatter them, turn neat stratigraphy into scrambled hints. And all of this is happening in water that is often dark, cold, and difficult to work in. Visibility on many continental shelves is a few meters at best. Currents can be strong enough that divers have to cling to guide ropes to stay in place. Every minute underwater requires planning, equipment, safety protocols, and money. An excavation that would be routine on land becomes logistically complex and expensive as soon as it's under even 10 meters of seawater. At 50 meters, you're relying on specialized mixed gas dives or remotely operated vehicles. At 100, human divers are largely out of the question. That difficulty filters what we're able to see. Underwater, some things survive beautifully. Stone tools are essentially immortal at these timescales. Flint, chert, obsidian, basalt. None of it cares about salt water. If it's not physically broken or transported, it can sit in marine sediment for 20,000 years and look almost exactly as it did when someone last used it. Large concentrations of shell, if they were buried quickly, can also persist as tight, coherent middens. Bones can survive, especially in low-oxygen, fine-grained muds. In exceptional cases, even trackways, pollen, and microscopic plant remains are preserved in drowned peat layers. But the fragile part of human life, the part that would tell us most about daily existence on those lost coasts, fares much worse. Wood decays unless it's buried in anoxic conditions. Basketry, nets, fish traps made of stakes and woven branches, house frames, fences, corrals, boats, rafts. All the infrastructure of a shoreline economy tends to vanish. Fibres, textiles, cordage, the things that tie and bind and carry dissolve into nothing. Plant foods leave few traces unless they're charred. Even animal remains can be selectively removed by bored crabs and burrowing worms. What's left is the durable skeleton of a culture without its flesh. On top of that, shorelines are not static lines. They're moving bands. As sea level rose, wave action and tides migrated inland, eroding here, depositing there, drowning river mouths and backflooding valleys. An archaeological layer that was once on dry ground might first be attacked at the erosional front, then, if any of it survives, find itself buried under a wedge of sediment as the active shoreline passes by. Drowned estuaries can stack multiple generations of landscapes on top of each other, an old river terrace, then an early estuary marsh, then a lagoonal mud, then the modern seafloor. Each step of that transformation has the potential to both destroy and protect different parts of the record. The result of all these processes is what you could call a survivor record. Inland rock shelters, caves, and high terraces look overwhelmingly like the whole story of late Ice Age and early Holocene life simply because they're what the planet preserved accessibly. They're the quiet corners that escape the worst of the rising water, the grinding surf, the modern trawl nets. It's easy to forget, staring at a map of known sites, that we're seeing a sample filtered not by where people actually preferred to live, but by where their traces avoided being drowned, shredded, and buried beyond economical reach. Archaeologists are not blind to this. Over the past few decades, a suite of methods has started to open those drowned landscapes, at least in outline. Multi-beam sonar can map the seafloor in high resolution, revealing the ghost shapes of old river channels, terraces, and shorelines tens of meters below the waves. Sub-bottom profilers send sound pulses down into the sediment and read the echoes, tracing buried layers and ancient land surfaces hidden beneath mud. Coring lets researchers pull up narrow cylinders of that buried history, peat over sand over gravel, each change marking a different phase of environmental transformation. When something looks promising, a paleosurface at the right depth and age, a concentration of shell, an odd acoustic reflector, teams can send divers or remotely operated vehicles down to take a closer look, recover artifacts, or document features in place. These tools are powerful, but they're still selective. We're not scanning every continental shelf in millimeter detail. We're targeting areas we already suspect might harbour sites, based on reconstructed sea level curves, known ancient river systems, and what we've learned from the few submerged sites that have been found so far. The picture is growing clearer, but it's nowhere near complete. This is where a certain kind of caution is important. Saying that our current record is biased toward inland survivors is not the same as saying there must have been an advanced, global coastal civilization wiped clean by the sea. Absence of evidence on the seafloor is not evidence that such a thing never existed. But the reverse is also true. The difficulty of looking underwater is not proof that anything we imagine must be hiding there. What the drowned coasts really offer is a vast, still largely unread archive from one of the most dynamic periods in human history. As we slowly learn to read it, the story of who we were at the end of the Ice Age is likely to change in ways we can't yet predict. If we wind the clock back to the very end of the Ice Age, the world was not sliding gently and predictably into the climate we know today. It lurched. By about 14,700 years ago, global temperatures had started to climb out of the last glacial maximum. Ice sheets were shrinking. Glaciers were in retreat. Sea level, which had been more than 100 meters lower than today at the peak of the Ice Age, was rising in pulses. For a few thousand years, things looked like they were on a one-way path toward warmth. And then, around 12,900 years ago, the planet snapped back. This interval is what scientists call the Younger Dryas, named after a little Arctic alpine flower whose pollen suddenly reappears in European lake sediments. It marks a return to much cold conditions right when the Great Thaw seemed well underway. In many parts of the Northern Hemisphere, temperatures appear to have dropped back to values not far from glacial conditions. In ice cores from Greenland, the shift looks almost like a cliff. Oxygen isotope ratios swing toward cold in what, on the graphs, is essentially a vertical line. In terms of global climate, the Younger Dryas lasted until about 11,700 years ago. On a human scale, that's roughly 40 generations of people living through a world that, from their perspective, had betrayed them. Now, if you lived then, you wouldn't have been watching isotope graphs. You'd have been watching rivers freeze for longer each winter, the tree line creeping downslope, animals changing their ranges, plants you relied on failing more often. The suddenness we see in layered ice and mud might have translated into a few hard years that never quite let up, followed by a long plateau of harsher conditions. In some places, the shift might have been brutally obvious. In others, it might have been a drawn-out tightening of the ecological noose. For people clustered along rivers, lakes and coastlines, those changes were not abstract. Late Ice Age hunter-gatherers were already experimenting with rich aquatic environments. Some were building economies around salmon runs, shellfish beds, estuarine wetlands, migrating waterfowl. These systems are wonderfully productive when everything lines up. They're also exquisitely sensitive. A colder climate can change snowpack and melt timing upstream, reshaping flood pulses and the way sediments move. River channels can shift, cut new paths, abandon old meanders. Estuaries can flip from brackish nurseries full of fish to muddy flats, starved of the right mix of nutrients. Sea ice can expand along coasts, blocking access to open water at critical times of year. The temperature of nearshore waters can alter which shellfish thrive and which simply disappear. If your group had invested generations of knowledge into reading one particular river delta, one specific stretch of tidal flats or reed-lined lagoon, that kind of reorganization would hit hard. The weirs don't catch what they used to. The familiar spawning runs don't arrive. The birds take a different flyway. You can adapt to a point, shift seasons, switch prey, retool technology, but eventually the cost of staying outweighs what the landscape offers. That's one of the quiet ways abrupt climate turns show up in the archaeological record. Not as scenes of disaster, but as absences, sites abandoned, traditions broken, tool types and food remains fading out in one region and appearing, a little later, somewhere else. At the same time, sea level was still climbing. The Younger Dryas didn't stop the oceans. It slowed some of the very rapid meltwater pulses, then toward its end and immediately after, appears to have framed some of the fastest. One of the best known of these is what geologists call meltwater pulse 1b, somewhere around 11,500 to 11,300 years ago, depending on which sea level curve you use. It wasn't as enormous as the earlier Pulse 1a, but we're still talking on the order of several meters of global sea level rise compressed into a few centuries, maybe less. On some coasts, that could mean shorelines marching inland a dozen meters or more in a single human lifetime, swallowing low-lying plains, marshes and deltas in what, to the people living there would have felt like a relentlessly encroaching sea. Now, layer those processes together. A cooling snap that reorganizes river flow and precipitation. Shifts in vegetation zones that change where game animals can overwinter. Sea level pulses that redraw estuaries and flood coastal flats. All of it set against a backdrop of people who had spent the preceding millennia learning to exploit exactly those edge environments. It's not hard to imagine what that would have looked like from ground level. Families packing up seasonal camps a little earlier each year. Fishing places slowly failing. Stories about an old village site out there beyond the current shoreline, now underwater at every tide. Knowledge of once reliable clam beds that are now in the surf zone, churned and scattered. Elders remembering a coastline that the children will never see. For archaeologists, the Younger Dryas sits at a pivotal hinge. In some regions, it seems to correlate with bursts of movement, groups pushing into new territories, trying out different subsistence strategies, reconfiguring toolkits. In others, it looks like contraction, populations pulling back into refuges where resources remained somewhat dependable. Both patterns make sense if you imagine hundreds of small societies, each with its own microecology, responding to the same broad climate turn in locally specific ways. The mechanisms behind the Younger Dryas are still debated. Many researchers point to disruptions in North Atlantic Ocean circulation, immense floods of glacial meltwater pouring into the wrong places, shutting down or weakening the currents that carry heat north. Others have proposed different triggers, from complex atmospheric feedbacks to more speculative ideas like distant impacts. What's clear is that the response was not uniform. Some regions seem to have been hit with intense cooling and drying. Others experience shifts in seasonality more than absolute temperature drops. A few areas may even have seen relative climatic improvement as circulation patterns rearranged rainfall. That unevenness matters when we think about human societies. Sudden is a slippery word in climate science. In an ice core, it can mean a decade. For a village depending on a single salmon run, 10 bad years in a row might be all it takes to force abandonment. For a group whose camp sat on a low terrace at the head of an estuary, a couple of meters of sea level rise spread across a century could drown not just their home, but every ancestral burial ground and shell mound they knew. When you bring these pieces together, the Younger Dryas cold reversal, the meltwater pulses bracketing it, the wobbly stepwise rise of the seas, you start to see how big environmental change can quietly erase entire communities without leaving dramatic signatures. No towering ruins, no smoking craters, just shorelines that no longer exist, deltas that migrated, wetlands that turned to bays, and the material traces of ordinary lives now lying under 10, 20, or 50 meters of water. From our vantage point thousands of years later, it's tempting to reserve words like catastrophe for singular, spectacular events. But for the people living through the end of the Ice Age, the catastrophe may have been this, that the very places which offered the richest, most reliable food, the coasts, the estuaries, the great river mouths, were also the ones most exposed to every twitch of climate and every surge of the rising sea. Those are exactly the landscapes we'll turn to next. Some of them we can still partially reconstruct. Drowned plains that once linked islands to continents, wetlands that were once dry steppe. Others remain mostly speculative, traced only by faint bathymetric contours and scattered finds. All of them sit on the moving boundary between ice, ocean and land, where sudden climate turns had the power not just to stress societies, but to remove their homelands from the map entirely. If you want a concrete example of what that kind of vanishing world looks like, you don't have to imagine it entirely from scratch. You can go to the floor of the North Sea, at least on a map, and look at a place archaeologists now call Doggerland. Today, if you glance at a modern atlas, Britain is an island. The English Channel and the North Sea seem like permanent fixtures, the natural boundary between the British Isles and mainland Europe. But for most of the last ice age, and well into the period when people like us were already living there, that water was land. Picture a broad, low-lying plain stretching from what is now eastern England across to the Netherlands, Germany and Denmark. Instead of grey waves, there are shallow river valleys winding toward a distant coastline somewhere out near the edge of the continental shelf. Where the modern map shows a shipping lane, there might have been reed-fringed marsh, patches of birch and pine, and herds of animals moving between drier ridges. That was Doggerland. At the height of the last glacial maximum, around 20,000 years ago, global sea level was roughly 120 metres lower than it is now. The North Sea basin was largely dry land, interrupted by rivers draining the melting ice sheets to the north and east. As the climate warmed and the ice retreated, the ocean crept back in, but it didn't do it all at once. For thousands of years, Doggerland persisted as an enormous, swampy, changing heartland between Britain and the continent. By about 11,000 to 10,000 years ago, at the tail end of the Younger Dryas and the beginning of the warmer Holocene, sea level in the North Sea region was still perhaps 40 to 60 metres lower than today. The shoreline lay far out beyond the current coasts. Britain was not yet an island. People could walk, in principle, from what is now Norfolk, across a patchwork of river crossings and wetlands, to what is now Denmark, without ever seeing an open sea. The drowning of Doggerland was a drawn-out process. Different reconstructions give slightly different timings, but most suggest that major parts of the plain were being lost between about 10,000 and 8,000 years ago, as meltwater pulses fed the rising ocean. By around 9,000 years ago, much of the central lowland was flooded into a broad bay. By roughly 8,000 to 7,500 years ago, only higher ridges and hills remained as islands and peninsulas. Sometime after that, Britain finally became physically cut off, the last land bridges going under as the English Channel and the southern North Sea joined up. On modern charts, you can still see the ghost of it. Doggerbank, a shallow plateau in the middle of the North Sea where the water is only 15 to 30 metres deep, surrounded by much deeper channels. That bank is part of the drowned landscape. We know it was once dry because fishermen dragging nets and trawls across those shallows have been pulling up fragments of that old world for more than a century. Pieces of peat, dark and fibrous, that formed in long-vanished marshes. Tree trunks, waterlogged oak and pine, from forests that grew on land now drowned. Mammoth bones, reindeer antlers, the remains of aurochs and red deer and wild horses, collected from the nets and sometimes kept as curiosities. Mixed in with the animal fossils every so often, there are unmistakable signs of people. Flint blades and scrapers, cores and flakes, barbed antler points. These are tools from the late Upper Paleolithic and Mesolithic, made by hunter-gatherers who used Doggerland's rivers and wetlands long before they lay beneath tens of metres of salt water. The record isn't just in random finds. In recent decades, scientists have been able to treat the North Sea like an oil company would, running seismic surveys, bouncing sound waves off the seabed and the sediment beneath it, building three-dimensional models of buried valleys and ancient shorelines. Those models show river systems carved into the old surface, complete with tributaries, floodplains and terraces. In some cases, cores drilled into these buried landscapes bring up pollen and plant remains that tell us about the vegetation. Open steppe giving way, over time, to mixed woodland as the climate warmed. Put together, the picture is surprisingly vivid. Doggerland wasn't a featureless expanse. It was a mosaic of habitats. Broad tundra plains during the coldest phases, dotted with low shrubs and hardy grasses. Later, as temperatures rose, patches of birch and willow along river corridors, then hazel and oak spreading across drier ground. Extensive wetlands in the low areas, peat bogs, fens, sedge-lined pools, rivers braided and meandering, with oxbow lakes and backwaters rich in fish. For human groups living there, it would have been a kind of paradise, at least in good years. Migrating herds crossing the open grasslands, waterfowl crowding the marshes, salmon and other fish running up from the distant sea along networks of rivers and streams, edible plants along the floodplains, raw material for tools and shelters, and for a long time, no great obstacle to movement between what we now think of as separate countries. But the very qualities that made Doggerland attractive also made it vulnerable. A low, flat plain only a few meters above sea level does not have much buffer when the ocean starts to rise. Each incremental increase in global sea level would have translated into floods pushing further inland, storm surges biting deeper into the marshes, salt water intruding into freshwater systems. From the ground, this probably wouldn't have felt like a single apocalyptic flood. It would have been more like a series of thresholds, a hunting camp near a river mouth that, a few generations later, was permanently waterlogged, a favourite ford that became too deep to cross safely most of the year, a cluster of burial mounds on a low knoll that ended up as a small island in a widening estuary. Communities would have adapted as long as they could, shifting camps upslope, learning new fishing grounds, tracking game as it altered its routes. But as the sea rose, Doggerland would have fractured. Continuous territories broke up into peninsulas and islands. Groups that once could visit each other on foot found themselves separated by growing channels. What had been a broad connective plain between Britain and Europe slowly turned into an inland sea that isolated them. There may also have been sharper shocks layered on top of this long, slow encroachment. Around 8,200 years ago, a massive submarine landslide off the coast of Norway, known as the Storegga Slide, sent a tsunami rolling across the North Atlantic margins. In some coastal areas of Scotland and eastern England, there are sand layers and damaged peat deposits that look very much like the traces of a large wave washing far inland. If Doggerland still had low-lying settlements and camps at that time, and the timing overlaps with its last stages, such a tsunami could have drowned entire tracts of already shrinking land in a single day. We can't yet say with certainty how many people lived on Doggerland at its peak, or how exactly they experienced its loss. The sites we have are mostly chance discoveries, not systematic excavations, but the scattered tools, the trawled bones, the mapped rivers and peat beds all point to the same conclusion. For thousands of years there was a real, inhabited landscape where the North Sea now lies, a place where families told stories, tracked seasons, buried their dead, and watched over generations as the horizon of their world shifted inland. Doggerland is just one example, in a relatively well-studied corner of the world, of how much can be erased when seas rise over flat continental shelves. It raises an obvious question. If this much complexity has been reconstructed from a few fishing nets and seismic lines in the North Sea, what might be waiting on other submerged plains, in parts of the world where the water is warmer, the sediments more mobile, and the search has barely begun? When you zoom out from Doggerland and stop thinking in terms of individual place names, another pattern comes into focus. The parts of that landscape that look most inviting on a reconstruction map, the drowned river mouths, the marshy embayments, the low deltas, are exactly the kinds of places that tend to draw hunter-gatherers everywhere. Wetlands, estuaries and river mouths are biological amplifiers. Fresh water, carrying nutrients downstream, meets slower moving or still water where sediments settle out. Sunlight, shallow depths, and a continuous supply of food from upstream turn these zones into nurseries for fish, invertebrates, birds, and mammals. For people without agriculture, that means something very simple. If you want predictable calories in a changing climate, you go where the water spreads out. That's why, when archaeologists look at modern foragers living in river deltas, tidal flats, mangrove swamps and floodplains, they often see groups with relatively stable populations and elaborate seasonal routines. The landscape may look messy and chaotic, all mud and reeds and shifting channels, but to people who know it well, it is structured. Different patches come into their prime at different times of year. A sandbar that is bare at low tide may be thick with shellfish. A backwater that looks stagnant in summer may be full of spawning fish in spring. A reed bed that seems impenetrable might hide nests of eggs when the waterfowl are breeding. Daily life in a late Ice Age or early Holocene coastal plain probably revolved around those subtleties. Imagine a small community, perhaps a few extended families, with a territory centred on a river that wound its way out across a broad shelf toward a distant, then lower sea. In winter, they might cluster in more sheltered camps on slightly higher ground, using stored fish, smoked meat, and collected nuts. As the thaw came, they would fan out along the floodplain, following runs of spawning fish upstream and harvesting early plants in the damp soils. Later in the year, attention would shift toward the estuary. People would set simple fish traps, lines of stakes guiding fish into woven funnels, or stone structures that only really functioned when the tide moved just so. Children and elders might gather shellfish from the exposed mudflats, prying up clams and mussels, picking through piles of oysters along the edges of tidal creeks. Others would go after waterfowl, using snares, nets, or carefully timed drives to take advantage of migratory flocks resting in the marshes. In many such societies, the calendar is not measured in numbered days, but in the arrival of particular fish, the ripening of specific berries, the timing of bird flights. A year might mean the sequence of movements from winter camp to spring fishing sites, to summer shellfish grounds, to autumn nut groves. That sort of seasonal round, repeated over generations, can be remarkably sustainable, and it leaves its mark on the landscape in quiet ways. Well-trodden paths along levees, small clearings on knolls, repeatedly used hearth sites at the edge of freshwater pools. The material culture that supports this kind of life is often exactly the kind that vanishes when sea levels rise. You don't need stone walls or monumental architecture to thrive in a wetland. You need things that float, flex, and bend. Lightweight shelters built from poles and thatch, re-erected year after year on the same favoured ground. Fishing gear made of stakes, wattle fences, and woven baskets. Nets spun from plant fibres, sometimes weighted with small stones but mostly just a mesh of organic cord. Dugout canoes or simple rafts shaped from logs with stone and fire, left pulled up on banks or tied to stakes when not in use. Storage baskets, fish weirs, drying racks, platforms raised above periodic floods. Almost all of it is perishable. In a dry cave you might get lucky and find a fragment of rope from 10,000 years ago. In a wetland that later drowned under salt water and shifting sand, those fibres are more likely to dissolve or be buried beyond easy reach. What we tend to recover instead are the harder pieces, a few flint blades from butchery sites, a scatter of stone tools on what used to be a campsite, and piles of shells where people sat and ate and tossed the remains. Shell middens, essentially ancient rubbish heaps of discarded shells mixed with bones, charcoal, and broken tools, become some of the most visible signatures of this way of life. On modern coasts, they often sit just above the high tide line. On lost coasts, they can lie tens of metres below the surface, sealed under layers of silt. For archaeologists working offshore, the first step is often to find the ghost of the river itself. Using sonar and seismic methods, they map paleochannels, buried riverbeds now under marine sediments. Those channels trace where freshwater once flowed. Along them, they look for subtle changes in sediment that might indicate old floodplains or levees, and for buried soils, horizons where plants once grew and people might have camped. Where conditions are right, a core pulled from such a buried surface can yield ancient pollen, bits of charcoal, traces of freshwater diatoms. In rare cases, it might even intersect a shell layer thick enough to be a midden. Each of these is a hint, a point on an invisible map of human use. What's striking is how ordinary all of this is. We're not talking about lost empires with gleaming harbours and stone quays. At least there's no good evidence for that on these early Holocene plains. We're talking about small bands and villages, maybe a few dozen people each, repeating their seasonal movements, tending fish traps, repairing nets by the evening fire, teaching children how to read the currents. Yet when the shoreline itself moves, when the river mouth that anchored the seasonal round becomes a lagoon, then an arm of the sea, then a patch of sea floor, those ordinary lives can become almost impossible to reconstruct. A camp that turned into an island for a few centuries before finally eroding away might leave nothing accessible at all. Place names vanish. Sacred spots favoured for generations are reduced to a thin, anonymous layer of sand and gravel. That's the quiet tragedy of drowned wetlands and river valleys. They were probably among the busiest, most densely used parts of late Ice Age and early Holocene landscapes, and yet, under modern water, they are some of the hardest to study. The result is a skewed view of the past. We see the inland camps that happen to be on higher ground, the caves and rock shelters that never flooded, while a whole parallel world of low, wet, highly productive country lies blurred beneath the waves. Doggerland offers a glimpse of that world in the North Sea. Elsewhere on the planet, the drowned plains are larger, the water deeper, the sediments thicker, and in some regions the scale of what has been lost is almost continental. Nowhere is that more true than on the vast, submerged shelf of Southeast Asia. During the last glacial maximum, about 20,000 years ago, sea level was something like 120 metres lower than it is today. In some places, that just meant the shoreline was a bit farther out. In Southeast Asia, it meant something else entirely. If you could drain the seas around Indonesia and Malaysia down to that Ice Age low stand, you wouldn't see an archipelago. You'd see a continent. The Sunda Shelf is a broad, shallow platform of crust that today lies mostly under 40, 50, maybe 70 metres of water. When the oceans were locked up in ice, that whole area, stretching from mainland Southeast Asia down past what are now Sumatra, Java and Borneo, was dry land. Rivers that are now separated by hundreds of kilometres of sea ran together into joined systems, meandering across wide floodplains before finally reaching a coastline far out toward what is now the Java Trench. Estimates vary, but the exposed plains of Sunda may have covered more than 1 million square kilometres at their peak. That's an area comparable to Western Europe, or to a third of Australia, not counting the high islands. Today we see fragments: Peninsular Malaysia, southern Vietnam, the Thai coast, the big islands of Indonesia. In between, where we picture blue water on the map, there used to be low country, swamps, forests, estuaries, lakes, and braided river deltas. If you were one of the humans living in this region during the late Pleistocene, that interior sea of land would have shaped almost everything about your world. Instead of island hopping across dangerous channels, you could have walked from what is now Vietnam to what is now Java without ever seeing the open ocean. The South China Sea was a gulf, not a vast sea. The Straits of Malacca were a valley. The Java Sea was almost entirely land, dotted with lakes, crossed by rivers, edged by marshes and mangroves. Those rivers would have acted as long, gentle migration corridors. Game animals, deer, pigs, bovids, would follow the gallery forests along their banks. People would follow the animals and the fish and the fruiting trees. Tall traditions and stories could travel hundreds of kilometres without anyone needing a boat. Then, slowly at first and then more quickly after about 15,000 years ago, the ice sheets began to melt in earnest. Sea level rose not as a smooth curve, but in fits and starts. Centuries of relative calm interrupted by pulses of faster rise when major ice margins collapsed. What had been a continental lowland turned into an enormous slow-motion floodplain. Rivers shortened as their lower courses drowned. Estuaries crept inland. Lakes merged with the encroaching sea. Places that had once been interior wetlands became tidal flats, then shallow bays, then open water. Some groups of people will have tracked the retreating shore, moving camp upslope season by season. Others may have found themselves stranded as long peninsulas turned into islands, then archipelagos, then scattered specks. For archaeology, this is both tantalizing and infuriating. If people were using those plains the way we might expect, congregating along river terraces, camping on low bluffs above floodplains, clustering around the mouths of big rivers, then the evidence of their lives is now tens of meters underwater. We can imagine what some of those signatures would look like. On an exposed Pleistocene river terrace, there might be scatters of stone flakes and cores where tools were made and resharpened. Along former levees, thin layers of charcoal could mark old hearth sites. Near the ancient coastline there might be shell middens dense with mangrove snails, oysters and crab claws, mixed with animal bone and fragments of grinding stones. Karst regions, limestone landscapes, around modern Borneo, Sumatra and the Malay Peninsula are full of caves and rock shelters that were dry during low sea level and sometimes still are. Offshore, their drowned counterparts may exist as flooded caves accessible only to divers, with stalagmites and flowstones that recorded ancient climate shifts drop by drop. On their floors, under a thin veil of marine silt, there could be buried surfaces where people once sheltered, napped stone, or buried their dead. Farther seaward, the old river mouths, now submerged deltas on the Sunda shelf, might preserve stacked layers of peat and silt, each one a snapshot of changing vegetation and water levels. Somewhere among those layers, archaeologists hope, there may be pockets where organic material survived. A worked piece of wood, a fragment of basketry, maybe even a preserved campsite sealed beneath the advancing sea. But this is one of the hardest places on Earth to look for such things. The very qualities that made Sunda so rich for human life now conspire against archaeology. Tropical rivers carry enormous sediment loads. Over thousands of years they have poured silt and clay out across the shelf, burying the old landscapes under meters of mud. Coral reefs thriving in the warm, shallow seas that flooded the lowlands have built upward, producing thick, irregular blankets of calcium carbonate that overgrow and obscure the Pleistocene terrain. Mangroves colonize shorelines and trap yet more sediment. On top of that, this is not a quiet, undisturbed seafloor. The Sunda shelf is crisscrossed by shipping lanes, oil and gas pipelines, and offshore platforms. Trawl nets rake the bottom in many regions. Near major ports and cities, pollution and dredging churn the shallow water. All of this makes it more difficult to find small, delicate traces of ancient human activity, and it means there are relatively few systematic underwater surveys compared to, say, the North Sea. A handful of projects have started to change that. Acoustic mapping of drowned valleys off Vietnam, coring programs in the Java Sea, exploratory dives in flooded sinkholes. But coverage is tiny compared to the scale of the drowned land. For now, much of what we say about human life on Sunda is inferred from the edges, from inland cave sites in Borneo and Java, from stone tool assemblages in peninsular Malaysia and Thailand, from genetic signals in modern populations that hint at long residence and complex movements through the region. Those lines of evidence point to a simple, powerful idea. The Sunda Plains were not an empty bridge that people rushed across to reach Australia. They were a homeland in their own right, occupied and reoccupied over tens of thousands of years by groups who fished its rivers, hunted its forests and watched its coast creep inexorably inland. Were there civilizations there in the later urban sense of the word, cities writing states, before the sea rose? There is no good evidence for that, and the timelines don't really favour it. But there could have been dense networks of coastal foragers and early cultivators, experimenting with plant management in fertile river valleys, developing maritime skills along the sheltered straits and channels that threaded the lowlands. A web of communities, not a single lost kingdom. When we look at a modern map and see the jigsaw of Indonesia and Malaysia, we're seeing the high points of that drowned world. The real connective tissue, the broad, flat, resource-rich country that joined them, lies hidden under warm, cloudy water. And yet, people did cross beyond it. At some point, groups moved off the Sunda Plains entirely, out across deeper channels toward a very different shore on the far side of another lost continent, Sahul and the first Australians. Sahul is one of those words that sounds mysterious until you realise it just means a land that used to be there. During the last glacial maximum, when so much water was locked up in ice that ocean sat roughly 120 metres lower than today, Australia wasn't an island. New Guinea wasn't an island. Tasmania wasn't an island. Together with the shallow platforms that now lie under the Arafura Sea, the Torres Strait and Bass Strait, they formed a single, sprawling landmass. Sahul. On a Pleistocene globe, the map would look strange to us. To the northwest, the Sunda Plains faded into shallow seas and island chains, and then, separated by deeper channels like the Makassar Strait and the Timor Trough, Sahul rose again, a big roughly triangular continent, its northern edge reaching almost to the equator, its southern edge extending down to the roaring Forties. For humans this mattered. Even at the lower sea stands there was never a continuous dry land bridge between Sunda and Sahul. To reach this southern continent, people had to cross water. Not necessarily vast amounts of open ocean at first, but real sea crossings. Tens of kilometres, then maybe more, hopping from high islands and headlands toward a faint line of land on the horizon. That tells us something important about the people who first reached Australia and New Guinea. By at least 65,000 years ago, based on some of the earliest widely discussed sites, like Majedbebe in northern Australia, humans were not just walkers and river travellers. They were builders of watercraft, readers of currents and winds, people who understood tides and shorelines enough to risk pushing off land with no guarantee of what lay beyond. In that world, coasts weren't just edges. They were highways and grocery stores and navigation charts all rolled into one. The shallow, gently shelving northern margins of Sahul would have offered everything a coastal group might want. Mangrove forests dense with fish, shellfish and crustaceans, shallow lagoons sheltering seagrass meadows and dugong, sand spits where turtles nested, estuaries where freshwater and saltwater mixed in endlessly productive mudflats. As sea level fell toward the glacial maximum, those coasts marched outward. River mouths lengthened, cutting across newly exposed continental shelf. Deltas built out into what is now the Arafura Sea. Northern Australia and southern New Guinea were joined by broad lowlands, an area known as the now drowned Arafura Plain and Carpentaria lowlands, encircling a shallow interior lake where the Gulf of Carpentaria lies today. If you'd stood on one of those late Pleistocene headlands and looked north, you might not have seen New Guinea as a separate thing at all, just a long rise on the horizon with low country stretching out toward it. People could have walked from what is now Arnhem Land to what is now Papua across coastal plains, salt marshes and river crossings, never needing to build a long-range seaboat again once that first barrier from Sunda was crossed. All along those shifting shores there would have been camps and gathering places, napping sites where stone was worked into tools along river terraces, short-term shelters tucked into dunes just behind the beach ridge, more permanent dry season bases on slight rises overlooking freshwater lagoons, and likely ritual or burial sites in places that held particular meaning, headlands, springs, distinctive rock outcrops. The problem is that a great many of those places are not where we can easily reach them now. As the last glacial period ended and ice sheets collapsed, sea level began to rise. Between roughly 20,000 and 7,000 years ago, the oceans climbed that full 100+ meters, not in a smooth, gentle slope, but through pulses. Times when shorelines might have moved tens of meters upslope in a human lifetime, and kilometers upslope over a few centuries. On Sahul's margins, that meant that those broad northern plains drowned. The coastline that once lay far out across what is now the Arafura Sea retreated first to the middle shelf, then toward the present line of mangrove and reef. The low saddle between mainland Australia and Tasmania went under, severing a southern land bridge. Bass Strait filled. The Torres Strait, once a pattern of rivers and wetlands, became a complex of channels and reefs. In some places the shoreline may have marched inland 40, 50, even 100 kilometres from its glacial maximum position. Any village of the late Pleistocene or early Holocene that clung to the then current coast and simply stayed put would, within a few generations, have found itself living in the surf zone. On land, what we see today is the remnant fringe, rock shelters and caves that were inland enough or high enough to stay dry. In northern Australia, sites like Majedbeb and Riwi preserve deep sequences of occupation, with stone tools, grinding stones, ochre and hearths that track tens of thousands of years of human presence. In New Guinea's highlands, early evidence of plant management and horticulture appears in valley floors that have never known marine flooding. These inland and upland records are extraordinary, but they are only part of the story. If people, like people everywhere else, favoured coasts, estuaries and lower river terraces, then the densest clusters of early camps, fish processing sites, shell middens and perhaps even semi-permanent villages may now lie under 10, 20 or 50 metres of water, scattered across what are now submerged shelves. What survives out there is hard to say. On some parts of the shelf, ancient river channels and lake basins are still etched into the seafloor, mapped by sonar and seismic surveys originally done for oil and gas exploration. Geomorphologists can trace the ghost courses of Pleistocene rivers flowing across the Arafura and Sahul shelves, carving valleys that later filled with mud and marine sand. Those paleo channels and the low terraces alongside them are exactly the kinds of landforms where archaeologists would expect to find traces of human activity, if those traces haven't been eroded away or buried too deeply. In a few cases, divers and coring projects have begun to probe these drowned landscapes. Submerged shorelines, ancient beach ridges, fossil coral reefs and cut terraces have been identified at depth that match known pauses in post-glacial sea level rise, like the still stands around 60, 40 or 20 metres below present. Each of those old coastlines would have been a favoured zone for human use at the time it lay at sea level. So far, direct archaeological finds on these offshore features around Sahul are sparse and tentative. The water is often murky, the distances are large, funding and logistics are challenging. As with Sunda, much of what we infer about submerged life comes from the edges. There is, however, another line of evidence that quietly points seaward: stories. Among many Aboriginal Australian and Torres Strait Islander groups, there are oral traditions that describe coasts where there is now sea, or journeys to islands that are now underwater banks, or the drowning of once dry lands by rising waters. Some of these narratives, when carefully compared with modern bathymetry and reconstructions of post-glacial sea level rise, seem to correspond to real features. A reef that would have been an island 12,000 years ago. A bay that would have been a valley before it flooded. researchers have suggested that a few of these story traditions may preserve cultural memories of shoreline changes going back 7, 8, perhaps even 10,000 years, far longer than written history in most parts of the world. The idea is controversial and has to be handled cautiously. Oral traditions are living things. They change, adapt, and take on new meanings over time. Alignments between a story detail and a mapped underwater ridge can be coincidence. We have to be wary of reading the past we want into tales that serve many purposes in the present. Even so, when a community whose ancestors have occupied a region for tens of millennia tells a story about a time when the sea lay far out, and when the hills now forming an island were once part of the mainland, and when you check the sea level curves and see that, yes, 11,000 years ago the shoreline would have been near the shelf edge there, it raises careful, quiet questions. Maybe some of the people who watch the sea creep into their fishing grounds, flood their ancestral campsites, and turn headlands into islands, also encoded those experiences into songs and narratives, maybe in a way that is hard for literate societies to appreciate. Some of that encoded knowledge has persisted alongside the stone tools and hearths we excavate on shore. For now, though, most of Sahul's ancient coasts remain unseen. The drowned estuaries of the Arafura Shelf, the old beaches off Arnhem Land, the vanished river mouths that once opened where Bass Strait now churns. These are research questions more than established chapters. Did early Australians build large, dense settlements along those shores? Or were they mobile foragers whose camps left only thin, scattered traces? How did their watercraft evolve once they no longer needed to cross wide, dangerous channels to reach new land? To what extent did coastal groups trade with, or diverge from, their inland neighbours? Those are the kinds of questions that sit today on the boundary between archaeology, geology, and the deep time histories held in indigenous knowledge systems. They remind us that when we look at the peopling of Australia and New Guinea, we're likely missing a whole belt of coastal life, erased not by catastrophe in a single night, but by 11,000 years of slow, relentless tide. And on the far side of the Pacific, another drowned corridor bears on the story of how humans spread into yet another continent. While Sahul's shelves vanished under warm tropical seas, a very different kind of land bridge was forming in the cold, windy high latitudes of the north, Beringia, and the coastal routes that may have carried people toward the Americas. Beringia is another of those names that sounds like a myth, but it too was once just a place you could walk across. During the colder phases of the last ice age, when sea level dropped 70, 90, even 120 meters below today, the shallow basin between northeastern Siberia and Alaska didn't hold a strait. It held a continent-sized platform of dry land and braided rivers. The modern Bering Strait is only about 55 meters deep at its shallowest. Lower the oceans far enough, and what is now choppy, ice-strewn water becomes a wide, windy steppe. Beringia. Picture a plain stretching from the Kolyma and Lena rivers in Siberia across to the Yukon and Mackenzie drainages in North America. Treeless in many places, but rich with grasses, herbs and low shrubs. Herds of mammoth, bison, horse and caribou moving along river valleys. Foxes, wolves and big cats trailing them. And along those same rivers, small bands of humans following the game, gathering plant foods, napping stone on river terraces. For much of the 20th century, the story of how people reached the Americas seemed simple. At some point late in the Ice Age, maybe around 13,500 years ago, the ice sheets in Western Canada pulled back enough to open an ice-free corridor between them. People living on Beringia, the story went, walked through this inland gap, spilled onto the Great Plains, and from there spread rapidly south and east. Archaeologists in North America built entire chronologies around this inland route. But as more evidence has come in, that neat story has frayed. We now know there were people south of the big North American ice sheets before that inland corridor was fully viable as a migration route. Sites like Monteverde in southern Chile, with dates around 14,500 years ago. Tentative evidence at even older sites, still debated pushing back further. Genetic studies suggest that the ancestors of indigenous peoples of the Americas may have been isolated somewhere in or near Beringia for thousands of years, perhaps between about 25 and 15,000 years ago, before expanding into the continents. This has led many researchers to look away from the ice-choked interior and toward the Pacific. The coastal migration idea proposes that some of the first people into the Americas didn't wait for a grassy highway to open through the glaciers. Instead, they moved along the edge where land met sea. From the Japanese archipelago and the Russian Far East, across Beringia's northern and southern shores, then down the Pacific Rim past the Aleutians, the Gulf of Alaska, and the coasts of British Columbia, Washington, and beyond. If they did, they wouldn't have been marching along the same coastline we see now. At the height of the last glacial maximum, around 20,000 years ago, large stretches of what is now the North Pacific continental shelf were dry land. Fjords were longer and deeper inland. Islands we know today were attached to the mainland by broad coastal plains. Kelp forests and rich upwelling zones would have hugged that ancient shoreline, offering fish, shellfish, sea mammals, seabirds, and edible seaweeds. Rivers pouring off the ice sheets would have created estuaries and deltas on those now drowned shelves. Any early camps strung along that route, short-term hunting sites, boat repair spots, small seasonal villages at river mouths, would have been built where the water met the land at the time. As the ice retreated and the seas rose, those same camps would have ended up tens of kilometers offshore, under tens of meters of water. That helps explain why interior sites, on higher ground and far from the shifting shoreline, dominate the early archaeological record, while clear coastal sites from the critical first phases of American settlement are so rare. It's not necessarily the people preferred the interior. It may simply be that coastal landscapes are the ones we've drowned. Dating this process is delicate. Different lines of evidence. Radiocarbon dates from sites, DNA from ancient and modern individuals, reconstructions of ice sheet margins, models of sea level change, all have their own uncertainties and margins of error. Some genetic models point to an initial split between Asian and ancestral American populations as early as about 25,000 years ago, with a standstill in Beringia before people moved south. Some archaeological interpretations see plausible human presence south of the ice before 16,000 years ago. Others urge caution, arguing that many proposed early sites are ambiguous. In that uncertainty, the seafloor looms large. Archaeologists and marine geologists interested in Beringia's coastal routes now spend a great deal of time looking not at maps of modern shorelines, but at bathymetry, the contours of the seafloor. They look for submerged paleo shorelines at depths that match known sea level low stands, say -40, -60, -100 meters. They trace drowned river valleys coming off what is now Alaska and the Russian Far East, searching for terraces and deltas that would once have been prime real estate for camps. Caves are especially prized targets. Along limestone coasts and in steep island chains, sea level rise can flood the mouths of caves while leaving inner chambers relatively undisturbed. Stalagmites and flowstones inside can record ancient climates. Sediments on the floors can trap charcoal, tools, even bones. On parts of the North Pacific Rim, divers and remotely operated vehicles are beginning to explore such flooded caverns. On the former Bering Land Bridge itself, much of the old surface is now in relatively shallow cold water. Some areas are blanketed in mud. Others still preserve the outlines of Pleistocene river systems in sonar images. Coring projects pull up layers of pollen, plant remains and animal bones, showing that this was once a habitable, even productive landscape. Whether it also holds preserved hearths and artifacts is an open question. The irony is that the very first footsteps into a new world may be the hardest ones for us to see. The people who stood on that vanished Beringian shoreline and watched unfamiliar land rising to the east may have left only the lightest traces, a scatter of stone flakes on a riverbank that is now 50 meters below the surface, a driftwood frame of a boat long since rotted away, a shell midden eroded by waves. As sea level climbed and the coast marched landward, those traces would have slipped beneath the waves, one beach ridge at a time. Later peoples moving along the new post-glacial shoreline built new camps, left new tools, told new stories about where they had come from. The original crossing faded into myth and then into silence, but the drowned edges are still there, lying under the grey waters of the Bering and Chukchi seas, hinting at a chapter of human migration we've only begun to read. And Beringia is not the only place where a once dry basin may have sheltered people during the Ice Age, only to vanish beneath the sea when the climate turned. Far to the south and west, another shallow depression flooded as the ice melted, creating what we now know as the Persian Gulf, and giving rise to the idea that a whole oasis civilization may have slipped under its waters. Today, when you look at a map, the Persian Gulf appears as a long, shallow tongue of water between Arabia and Iran. But if you roll sea level back by 70, 90, 100 meters, that water drains away. In its place, you don't get a chasm or a deep abyss. You get a broad, low-lying basin, the exposed floor of the Gulf, tilted gently down toward what is now the Strait of Hormuz. During the coldest phases of the last ice age, rivers that now empty into the Gulf would not have stopped at the present shoreline. The Tigris and Euphrates, winding down from the mountains of Turkey and northern Iraq. The Karun and other rivers crossing the Zagros from what is now Iran. Seasonal streams and wadis coming off eastern Arabia. All of them would have flowed across that dry basin, converging into a single trunk river that continued out through a narrower, more distant coastline toward the Indian Ocean. The Persian Gulf oasis hypothesis takes that basic geography and asks a simple question. If there was once a river-fed lowland here, with fresh water, wetlands, and a milder microclimate, could it have been a magnet for human groups? Models of past sea level suggest that for long stretches between about 70 and 15,000 years ago, large parts of the Gulf floor were exposed. At times, the basin may have held shallow lakes and marshes, fed by those big river systems. Freshwater springs could have bubbled up where groundwater met the surface. In a region where much of the surrounding land was arid or semi-arid, that would have been extraordinarily attractive. Instead of a modern shoreline with desert running straight into the sea, imagine belts of reeds, lagoons, and gallery forests tracking those rivers across the basin. Herds of gazelle and onager, migratory birds, fish crowding the channels, and along the banks, small human camps, shifting with the seasons, following water and game. This is still a hypothesis, not a discovered lost world. But there are kinds of evidence researchers look for. Sonar mapping of the Gulf floor has revealed buried river valleys, paleo-channels, carved into the sediments and now infilled, exactly where you'd expect former rivers to have run. Subtle ridges and depressions hint at old shorelines of lakes or marshes. In some places, cores pulled from the seafloor bring up layers rich in pollen, plant remains, and fine mud that look more like ancient lake deposits than open marine sediments. On the modern coasts around the Gulf, there's a noticeable clustering of early sites near those ancient river mouths. Late Pleistocene and early Holocene stone tools on terraces overlooking where the rivers now meet the sea. Shell middens and campsites that date to the period when the rising ocean was just beginning to invade the basin. It's as if people were already living close to a resource-rich lowland, and simply tracked the retreating edge of dry ground upslope as the water came in. Geologists and archaeologists also watch for signs of ancient springs, carbonate crusts, distinctive mineral deposits, or buried channels that might mark long-lived freshwater outlets on what is now the seafloor. A cluster of such features, combined with lake sediments and nearby paleo channels, would strengthen the case for habitable pockets within the basin. But big questions remain open. How green was this landscape, really, at different times? Was it a permanent oasis, or a patchwork of wetlands that waxed and waned with climate swings? How stable were the rivers as the ice sheets advanced and retreated, as global rainfall patterns shifted? And crucially, how many people could such a basin support? Dozens, hundreds, perhaps more. Some researchers see a tantalizing connection between this drowned lowland and the later rise of Mesopotamian riverine societies. Long after the Gulf flooded, around 10 to 6,000 years ago, we start to see increasingly complex communities along the lower Tigris and Euphrates, experimenting with irrigation, wetlands management, and intensive use of river resources. It's tempting to imagine a deep cultural memory of living in and around a great delta oasis, transferred upstream as the sea swallowed the old ground. But that's an association, not proof. The timeline is fuzzy. The archaeological record on shore is patchy. And the crucial piece, the basin itself during its dry phases, is mostly hidden under tens of meters of warm, often murky water. That's why the Persian Gulf oasis idea is valuable even in its uncertainty. It's a testable story that pushes research offshore. It motivates high-resolution bathymetric surveys, targeted coring along buried channels, and eventually careful underwater excavation on promising ridges and terraces. Each new core that shows ancient reeds instead of marine plankton, each submerged spring deposit, each pattern of early sites hugging the old drowned shoreline adds another pixel to the picture. Whether the Gulf Basin turns out to have been a dense heartland or just a modestly favourable corridor, it reminds us of the same lesson we've seen with Beringia and the Sunda Shelf. Some of the most important landscapes in our prehistory may now lie beneath shallow seas, and the Persian Gulf is not the only place where the Indian Ocean has quietly covered its tracks. To the east, off the coasts of India and Pakistan, other drowned plains and river mouths are beginning to come into focus. If you follow that drowned edge of the Indian Ocean eastward, the pattern continues. Today, India looks like a compact triangular peninsula pushing down into the sea. But during the last glacial maximum, when global sea level sat roughly 120 meters lower than it does now, that triangle was larger, much larger. Along much of the subcontinent, the continental shelf is relatively broad and shallow. Off western India, in the Arabian Sea, large tracts of seafloor lie within that critical band between about 20 and 100 meters below present sea level. Off the east coast, in the Bay of Bengal, river deltas reach out over similarly shallow ground. When ice sheets began to melt around 20,000 years ago, and the great post-glacial sea level rise kicked in, all of that low, flat coastal plain was fair game. The rising waterline marched inland decade by decade, century by century, drowning sandbars, estuaries and river mouths in slow motion. Shorelines that had once been tens of kilometers farther out shifted landward, sometimes by more than 100 kilometers, as the sea climbed through that last 2,120-meter window. Any human groups who preferred coasts, who camped by lagoons, fished tidal channels, or followed shellfish beds along sandflats, would have been living on landscapes that no longer exist. Those are now bands of seafloor just offshore, lying under tens of meters of water, invisible from the modern beach. Because of that, India has become one of the places where debates about submerged prehistory are loudest. You may have heard of the Gulf of Khambat, a broad, funnel-shaped inlet north of Mumbai where, in the early 2000s, A side-scan sonar survey picked up what looked like rectilinear patterns and mounded features on the seafloor at depths of around 30 to 40 meters. Some headlines at the time called this a lost city, even a drowned civilization older than Mesopotamia. But when scientists started looking closely, the picture became murky in a very different way. The Gulf of Kambat is an energetically hostile place for archaeology. Tides rip in and out. Currents are strong. The water column is thick with suspended sediment that makes visibility poor and disturbs the seafloor almost constantly. Hard surfaces get scoured, buried, and re-exposed. River systems deliver enormous loads of sand, gravel, and artifacts from upstream. In that kind of environment, it's easy for natural rock outcrops to erode into blocky shapes and linear ridges that look, on blurry sonar images, like walls, platforms, or foundations. It's also easy for isolated artifacts, potsherds, stone tools, carved fragments eroded from much younger onshore sites, to be washed out, tumbled along the bottom, and finally dropped far from their original context. Some of the material reported from Kambat really does look man-made. Worked stone, ceramic fragments, objects that belong to known cultural periods. But without clear stratigraphy, without seeing these things in place in undisturbed layers, sealed beneath dated sediments, it's almost impossible to say whether they come from a coherent ancient settlement on that exact patch of sea floor, or whether they are a time-mix sampler pack, delivered and rearranged by currents over thousands of years. That doesn't mean there were no ancient coasts out there. It just means we have to be careful how we interpret noisy signals from a harsh environment. Other work along India's margins has taken a slower, more methodical path. Off the southeast coast, near sites like Pumpuhar in Tamil Nadu, surveys have mapped submerged river channels and sand bodies at depths of 10, 20, even 30 meters. Geophysical data reveal buried channels that line up with modern rivers, suggesting older valley systems that once cut across a broader exposed shelf. Cores pulled from these features bring up sequences of estuarine muds, overlain by marine sands, a quiet signature of a shoreline migrating across the landscape as sea level rose between about 12 and 6,000 years ago. Along both the east and west coasts, researchers have identified paleo shorelines, old beach ridges and wave-cut terraces, now lying tens of meters underwater. Some are dated with radiocarbon from shell fragments. Others are bracketed using sea level curves. If you know that global sea level passed through minus 40 meters around 11 to 10,000 years ago, for example, and you find a beach ridge perched at that depth, you can begin to pin down when that coastline was active. Here and there, divers and dredgers have recovered stone tools and cultural material from near these submerged features. But the key difference from the more sensational claims is context. The best underwater archaeology near India now focuses on tying finds to well-mapped surfaces, dated sediments, and clear stratigraphic relationships. A stone tool in isolation on the seafloor is interesting. A stone tool embedded in an ancient soil layer, capped by estuarine muds, overlain by marine sand, with each layer dated independently. That begins to tell a coherent story. Misinterpretation is always a risk in this realm. Natural rock ledges can fracture into straight lines. Honeycomb weathering can mimic masonry. Bioerosion by boring organisms can create patterned pits that, at a glance, look like carved motifs. Strong currents and storms can sort pebbles into strangely regular clusters, or align debris along ripple crests that resemble roads or walls when seen only in plan view. To move beyond that ambiguity, researchers working off India's coasts emphasize a few tools. High-resolution multi-beam bathymetry to capture the true three-dimensional shape of the seabed. Sub-bottom profiling to see buried layers beneath the surface. Systematic coring to recover continuous sediment records from promising terraces, channels, and ridges. Careful laboratory dating, radiocarbon on shells and organic material, optically stimulated luminescence on sands, sometimes even uranium series methods on carbonate crusts. Most importantly, they stress transparent methods and open publication. If a sonar image seems to show a rectilinear feature, the raw data and processing steps need to be available for others to inspect. If artifacts are recovered, their exact positions, depths, and surrounding sediments need to be documented just as they would be on land. The more that kind of work is done, the more the broad outline comes into focus. During the late Pleistocene and early Holocene, as sea level surged upward through that last 2120-metre band, the subcontinent's shorelines were not fixed lines on a map. They were moving targets, sweeping back and forth over wide shelves. Rivers carved deeper valleys across the exposed plains. Deltas built out, then were truncated. Estuaries formed, migrated, and drowned. Somewhere on those vanished plains, people almost certainly walked, camped, fished, and left traces of their lives. The task now is to find the few places where geology, preservation, and luck have conspired to keep a sliver of that world intact. Enough to read, layer by layer, before we move on down the coast to other island chains and continental edges where similar stories may be hiding under the waves. If we keep drifting east, following that drowned margin of the Indian Ocean around into the Pacific, the next place where these questions flare up is Japan. Modern Japan looks like a steep chain of islands rising abruptly from deep water. But that's a bit of an illusion created by the present sea level. During the last glacial maximum, when the seas stood those 120 metres or so lower, wide tracts of what is now seafloor were dry land. Shallow shelves extended off Honshu and Kyushu. Narrow straits were tighter or even closed. Some islands that feel isolated today were parts of larger peninsulas, and scattered along those submerged margins are features that have become almost mythic in certain circles. The most famous is near Yonaguni, at the far southwestern end of the Ryukyu archipelago, not far from Taiwan. At depths between about 5 and 25 metres there, divers encounter massive stone steps and terraces, broad platforms, sharp edges, flat faces, and what look like stairways rising and falling into the blue. Photographs and videos of Yonaguni's monument make it easy to see why people get excited. To an untrained eye, it looks eerily like a ruined pyramid or a weathered ziggurat sitting on the seabed where no one expected it. From there, the stories almost write themselves: a lost city, a forgotten Ice Age civilization, a culture that built in stone before the end of the last glaciation, only to be swallowed by the rising sea. But when geologists and underwater archaeologists have gone to Yonaguni and taken a slower look, the picture becomes more complicated and in some ways more interesting. The bedrock in this region is mostly sandstone and mudstone laid down in horizontal or gently tilted layers. These rocks have planes of weakness, bedding planes, joints, and fractures that tend to break along straight lines and right angles. In a high-energy marine setting, with powerful waves and currents, those weaknesses are exploited again and again. Blocks sprawl off, leaving fresh, flat faces. Corners snap away along joint sets, producing crisp edges and step-like ledges. Given enough time, that kind of erosion can create shapes that are uncannily geometric. Long rectilinear blocks, flat-topped terraces, deeply incised grooves that mimic cut channels. At Yonaguni, many of the staircases line up perfectly with the regional fracture patterns in the bedrock. The walls and platforms follow natural bedding planes. So how do you tell the difference between geology doing its best imitation of architecture and genuine human workmanship, especially underwater? Archaeologists and geologists use a few cautious criteria. One is tool marks, repeated patterned scars that match known methods of quarrying or dressing stone. Another is context, masonry that appears in association with clear cultural material, potsherds, bones, hearths, or worked tools embedded in undisturbed layers. They also look for systematic departures from what the rock would do on its own. For example, blocks that have been rotated or stacked against gravity, joints that have been cut across rather than along natural fracture sets, features that align to astronomical or cardinal directions in ways that are statistically unlikely to be random. At Yonaguni so far, those lines of evidence have been thin. The terraces and ledges are striking, but they can be plausibly explained by the known behaviour of layered sandstones under wave attack. Where isolated artefacts have been reported in the broader area, they lack the kind of sealed, datable context needed to tie them directly to construction on those specific ledges. That doesn't mean no one ever used the site. It's entirely possible that when sea level was lower, and those platforms were closer to or above the waterline, people fished from them, camped near them, or even modified small areas. The question is not whether humans ever touch these rocks. It's whether the entire complex is a deliberate monument from some unknown civilization. On current evidence, most specialists lean toward a primarily natural origin, perhaps with minor human use or modification on top. Stepping back from Yonaguni helps. Japan's coasts, like India's, preserve a quieter, more cumulative record of life along shifting shorelines. Around the main islands, researchers have mapped submerged paleo shorelines at depth of 10, 20, 40, sometimes 60 metres. Some are fossil beach ridges, low, parallel sand and gravel bars that run along the shelf. Others are wave-cut benches and terraces carved into bedrock when the sea stood temporarily still during pauses in the post-glacial rise. Radiocarbon dates from shells on these features, combined with global sea level curves, suggest that many were active between roughly 15,000 and 6,000 years ago, as the oceans climbed steadily toward their present height. During that time, the distances between the Japanese islands and the Asian mainland were shorter. The Tsushima Strait and other channels were narrower and shallower, sometimes studded with low islands and exposed banks. Human groups in this region adapted early and intensely to those coastal environments. Japan's Jomon culture, which begins to appear in the archaeological record by about 14,000 years ago, is famous for some of the world's earliest pottery. But it is also known for enormous shell middens, heaps of discarded shells, fish bones and other food remains that line ancient shorelines. Many of those mounds now sit a little inland from the present beach, marking Holocene high stands and earlier coastal positions. Others, very likely, are now under shallow water on the continental shelf, drowned as estuaries widened and bays flooded between about 10,000 and 7,000 years ago. Surveys off parts of Honshu and Hokkaido have begun to find hints of this. Submerged forests where tree stumps still stand in place beneath a few meters of water, peats and soils buried under marine sediments, and occasional lithic artifacts emerging from eroding banks. As with India, the clearer stories come when artifacts are tied to mapped landforms and dated layers, rather than to isolated discoveries on the seabed. The debates around Yonaguni and around other proposed underwater ruins in the Ryukyus can be read as a kind of cautionary tale. It's entirely natural to be drawn to spectacular shapes in deep water. Our brains are excellent at recognizing patterns even when none were intended. But the same curiosity that pulls us toward mystery can also push us toward stronger standards of evidence. In a way, that balance between wonder and rigour is the thread running through all of these submerged coast stories. If we insist that every straight line on the seafloor must be a lost temple, we will be disappointed and will miss the quieter, more pervasive evidence of real human lives erased by the sea. If we dismiss every unusual feature as just rocks, we risk overlooking genuine traces of early coastal cultures. Japan's drowned shelves remind us that we live at the end of a long, restless experiment in sea level. Over the last 20,000 years, the waters have risen, paused and risen again, turning headlands into islands, islands into shoals, and coastal plains into fishing grounds. Somewhere along those vanished Japanese shores, people stood, watched the tides, and built their own small worlds at the water's edge. We may never know the full extent of what was lost there, but by combining careful mapping, patient dating, and a willingness to entertain, but also to test, extraordinary claims, we can start to glimpse at least the outlines of that missing coastline before we drift on, past Japan's island arc, toward other basins where the sea has been just as busy rewriting the map. If we leave Japan behind and follow the old Ice Age shorelines west, across Asia and back toward Europe, we eventually come to a very different kind of sea. The Mediterranean is small on a global map, but in human terms it is enormous. This is one of the places where our species has been living, moving, and building for tens of thousands of years, maybe longer. It is ringed by coasts that have never really been stable, deltas that grow and sink, fault zones that lift and drop whole blocks of land, volcanic arcs that rise in centuries and collapse in a day. Put those two things together, deep time human presence and restless margins, and you get exactly what we find here. An unusually dense scatter of drowned shorelines and submerged sites, from the shallow shelves off Israel and Lebanon, to the harbours of Greece and Italy, to the low plains that once stretched off North Africa and the Adriatic. In some places the story is clearly post-Ice Age and almost gentle. Along parts of the Israeli coast, for example, early Holocene villages now sit under a few metres of water. At sites like Atlit Yam, radiocarbon dates cluster around 9 to 8,000 years ago, when global sea level was still climbing toward its present stand. Stonehouse foundations, wells, and even arrangement of stones interpreted as ritual features lie on what was once dry land, now about 8 to 12 metres below modern sea level. There, the mechanism is straightforward. As the ice sheets melted between about 11,700 and 7,000 years ago, the Mediterranean slowly invaded coastal plains and low terraces. People who had built close to the contemporary shoreline, taking advantage of wetlands, estuaries, and fisheries, found the sea creeping inland. Some communities moved, others left their walls and hearths to be silted over and preserved beneath the waves. Elsewhere around the basin, the picture is more tangled. In the central and northern Mediterranean, the weight of the vanished ice sheets on Europe and Scandinavia still echoes in the crust. During the last glacial maximum, that ice pushed the northern lithosphere down. Areas farther south, including parts of the Mediterranean margin, flexed upward in response. As the ice melted, that pattern began to reverse. Northern lands rebounded, while some peripheral regions experienced relative subsidence. Layered on top of that is isostatic adjustment to changing water load in the basins themselves, plus local tectonics along active faults. The Hellenic arc around Greece, much of western Turkey and stretches of Italy sit in a zone where plates converge, slide and twist. Over the last 10,000 years, some sectors have risen meters, others have dropped, sometimes abruptly during earthquakes. The result is that a single depth on the seafloor, a terrace at, say, 20 meters, does not necessarily correspond to the same date everywhere. In one bay, it might be an early Holocene shoreline from about 10,000 years ago. In another, it could be a classical harbour drowned by a few meters of subsidence since Roman times. Underwater archaeology here has to navigate that complexity, but when it works, the rewards are unusually concrete. Divers and remotely operated vehicles have documented stone walls, room layouts, and streets in places like Pavlopetri off southern Greece, where a Bronze Age town, probably active between roughly 5,000 and 3,000 years ago, now lies under 3 to 4 meters of water. In the Bay of Naples and along parts of the Bay of Pozzuoli, Sections of Roman waterfronts, piers and villas stand on submerged ground that has gently sunk under the influence of volcanic processes over the last 2 millennia. In shallower zones, cores and sonar surveys reveal buried river channels, peat layers, and old beach ridges that mark former coastlines from the early Holocene and late Pleistocene. On the Tunisian shelf, in the Adriatic and off the Rhone and Nile deltas, these drowned landscapes hint at broader coastal plains that would have been exposed when the sea stood tens of meters lower, especially before about 9,000 or 10,000 years ago. From a distance, it can be tempting to collapse all of this into a single story. The Mediterranean rose and old coasts sank. The reality is more like a palimpsest. Global sea level rise sets the general trend, but local uplift, subsidence and earthquakes constantly rewrite the details. An early Neolithic village and a Roman fish pond can end up at the same depth for completely different reasons. What makes the Mediterranean valuable in this broader puzzle is not just the number of sites, but the way they tie human remains, built structures, and clear dates directly to specific episodes of shoreline change. Here we can see the spectrum. At the shallow end, late Holocene and historical submergence, quays, breakwaters and temples slipped underwater by a few meters of land motion since about 3,000 years ago. Deeper down, early Holocene shifts, villages, fields and wetland edges abandoned between about 10,000 and 7,000 years ago as the post-glacial ocean advanced. Deeper still, beyond the reach of casual diving, the basal terraces and channels that mark where the Ice Age coast once ran, when sea level was 60, 80, even 100 meters lower, and very little direct archaeology has yet reached. Taken together, these layers turn the Mediterranean into a kind of laboratory for thinking about drowned coasts everywhere. They show that shorelines are not fixed backdrops for human history. They are moving archives. A harbour here, a village there, a buried lagoon somewhere else. All are pages from a book written partly in stone and partly in water. And if this relatively small, well-studied sea can still surprise us with entire quarters of ancient towns preserved under a few meters of water, it nudges us toward a quiet, unsettling thought. Along larger, less explored margins, whole chapters of coastal life from the end of the Ice Age may lie offshore, waiting, or already erased beyond recovery. From here, the question becomes less, did the sea take anything? And more, how exactly do we go looking for what it left behind? To answer that, we have to switch vantage points for a moment, from people on vanished coasts to the people who are trying to find them. Imagine starting not with a ruined wall or a scatter of tools, but with a blank seafloor, tens or hundreds of kilometers long, no signposts, no grid of streets, just depth, water, and mud. How do you even begin? The first layer of the toolkit is bathymetry, which is really just underwater topography. Research vessels send pulses of sound down to the seafloor and record how long they take to come back. Do that once, and you know a single depth. Do it millions of times along carefully spaced lines, and you can build a three-dimensional model of the submerged landscape. Ridges and basins, terraces and channels, old river mouths now under 40, 60 or 120 meters of water. Bathymetry gives you the broad shapes. To see texture on those shapes, researchers add side-scan sonar. Instead of just measuring depth beneath the ship, side-scan throws acoustic beams out to either side, painting the seafloor with sound. Hard surfaces like rock or old reef reflect strongly. Soft mud absorbs more. Subtle patterns emerge, sinuous lines where rivers once flowed, shore parallel bands that might be old beach ridges, isolated mounds that could be reefs, sandbars, or in rare cases built features. Then there is magnetometry. Many rocks and most human metals alter the local magnetic field slightly. Tow a magnetometer behind a boat, and it will register tiny anomalies. On post-Ice Age shelves, Those signals often come from buried channels, basalt outcrops, or later shipwrecks, but sometimes they help refine the subsurface map, outlining the path of a river or hinting at where erosion has cut into older strata. To look beneath the surface of the seabed itself, teams turn to seismic profiling. Low-frequency sound waves are sent down and bounce off layers of sediment and rock at depth. On the display, those reflections build up into cross-sections, stacked sheets of mud and sand carved by valleys, overlain by deltas, folded or faulted where the crust has moved. In those profiles, a drowned river valley might appear as a broad U-shaped incision cut 30 meters into older sediments, now partly filled and sealed. But maps and profiles only get you so far. At some point you need to touch the past. That is where coring comes in. A corer is simply a tube, sometimes a few meters long, sometimes 20, driven into the seabed to bring up a vertical column of sediment. Within that column, time is stacked, coarse river sands overlain by estuary muds, capped by marine silts full of shell fragments. Tiny fossils, pollen grains, and chemical markers let researchers identify environments. Freshwater swamp, brackish lagoon, open sea. Radiocarbon and other methods can pin dates to those transitions. Put all of this together, and you can start to reconstruct paleo shorelines. Global sea level curves, built from coral reefs and deep-sea records, tell you that at the last glacial maximum, around 20,000 years ago, the ocean stood roughly 120 meters lower than today. But local stories are never that simple. Some margins have been slowly uplifting, others subsiding. In places like Scandinavia, post-glacial rebound has raised old beaches high above current sea level. Elsewhere, sediment loading and tectonics have pushed coasts down. So, coastal scientists combine global curves with regional uplift or subsidence rates, often derived from dated shoreline markers on land. They adjust the base sea level line up or down and project it across the bathymetric surface. Where the adjusted sea meets the modelled land at a given date, you get a paleo shoreline. Step through time, and old coasts advance and retreat across the shelf like a slow-motion tide. Within that moving frame, some zones stand out as especially promising. Drowned river valleys, broad branching channels cut into the shelf are prime candidates. On land, people have always gravitated toward river mouths and estuaries. Fresh water, fertile floodplains, access to inland routes and marine resources all in one place. Sheltered bays, where waves lose their energy and boats can land easily, have the same attraction. If those features lay near an Ice Age shoreline, there is a reasonable chance people used them. Even more important is what has happened since. A good target is not just a plausible place where people could have lived, but one where later processes might have preserved their traces. Thick blankets of fine sediment conceal old ground surfaces, protecting hearths, tools, and organic remains from storms and currents. Seismic profiles and cores help identify those sealed surfaces, flat, continuous layers that once lay at the top, now buried under younger mud. In between these technical steps, there is a quieter layer to the search. The work takes time, patience, and often more resources than are easily available. Mapping a single stretch of continental shelf at high resolution can require weeks of ship time and expensive instruments. Permits are needed from coastal states. In some places, security concerns or protected habitats limit where you can survey or core. Visibility underwater is often poor. Divers and remotely operated vehicles may see only a few meters ahead. And beyond all of that is simple scale. Continental shelves ring the world. Many are tens of kilometers wide. Much of that area has never been examined in detail. Amid that vastness, it can be easy to feel as if the past might simply slip away, drowned not just by water, but by the limits of attention and funding. Before we go further, If you're enjoying drifting through this submerged deep time, this whole episode is based on research that I've woven into a longer written form. The Sleepy Time History book on lost shorelines and Ice Age coasts is available at sleepytimehistory.com, and for this week there's a discount if you'd like to sink a little deeper into the story at your own pace, when a promising area is finally surveyed. What counts as strong evidence is not just an intriguing shape on a sonar image, or a single artifact on the seabed. Researchers look for stratified contexts, layers that make sense in sequence, with cultural material lying on or within clearly defined ancient surfaces. They seek secure dates, radiocarbon ages on charcoal, bone, or peat tied directly to those layers, or other dating methods cross-checked where possible. They run repeatable surveys, multiple passes with sonar and seismic gear, independent teams confirming the same features, cores taken at different points, all telling a consistent story of environments and timing. Only when all of those lines converge, a modelled shoreline passing through a drowned valley, sealed surfaces in the right position, dates that align with the end of the Ice Age, and unmistakable human traces in place rather than scattered, do we begin to glimpse more than just a theoretical landscape. We start to see faintly the contours of real lives once lived along a coast that no longer exists, and even then we're only scratching the places where the evidence has survived. In the next part, we'll step back from the tools and ask a quieter, harder question. Of all the worlds the sea has taken, what might be gone forever, and what might still be waiting out there in the dark just beyond the surf line of our imagination? When you add it all up, the scale of what could be missing is sobering. For tens of thousands of years before the Ice Age ended, shorelines sat far out on the continental shelves. Sea level didn't rush upward in a single leap. It rose in steps, sometimes pausing for centuries, sometimes surging by 10 or 20 meters in a human lifetime when ice sheets collapsed. Every time the ocean advanced, it ate a strip of land that had been dry ground for generations, sometimes for millennia. Along those moving edges, people would have done what people always do. They would have built camps on low bluffs above the beach. They would have followed river mouths as they shifted across their deltas. They would have left layers of shell and bone, fire-blackened stones, broken tools, and footprints pressed into wet sand and peat. All of that, generation after generation, could easily have ended up under 20, 60, 100 meters of water. Not one site, not a handful. Entire belts of shoreline, tens of kilometers wide and thousands of kilometers long, ringing every continent. It is tempting, standing in front of that blankness, to imagine something grand. A vanished global civilization, cities mapped to the constellations, lost knowledge far beyond anything we can document on land from the same period. That story has a powerful pull. It speaks to a wish that the gaps in our record might be hiding something as dramatic as the ruins of Atlantis. But when we test that idea against the evidence we do have, it collapses quietly. By the time sea level began its final rapid climb, around 14,000 to 8,000 years ago, we can already see what inland societies were like. Small-scale, mobile or semi-sedentary groups. Stone tools, bone points, woven fibres, simple dwellings. No large-scale metallurgy, no writing, no monumental architecture that required tens of thousands of coordinated labourers. The genetic record shows expanding, mixing populations, but not the signatures you would expect from a single, globally integrated culture. If there had been chains of coastal megacities with advanced engineering, they would have drawn resources from far inland, mines, quarries, farms. Those hinterlands should still be visible. They are not. The inland sites we do find from the late Ice Age and early Holocene look like what you would expect from hunter-gatherers and early horticulturalists. Complex in their own way, certainly intelligent, but not plugged into some lost world-spanning system. So when we talk about what the sea has taken, We should keep both ideas in mind at once. The loss is probably huge. The shape of that loss is probably ordinary. What we can realistically hope to find, as the technology improves and the surveys multiply, are the traces of everyday coastal life. Seasonal camps on old dunes and headlands, shell middens, great mounds of oysters, clams and snails, now sealed under marine mud, fish weirs built of stone or wood, laid across tidal channels to funnel fish into traps, still visible on sonar as faint geometric lines, wooden stake alignments sunk into estuary mud, perhaps parts of platforms or walkways, simple dugout canoes buried in anoxic sediments, scatters of stone tools on what were once river terraces, peat beds full of preserved pollen and seeds, giving us the plants people gathered and the forest they moved through, even human and animal footprints impressed into ancient shore flats, like those found at Happisburgh in England or along the Gulf Coast, but now lying beyond the surf. In the best preserved patches, we might find drowned forests, tree stumps still rooted in place, ringed by the remains of hearths and post holes on the old forest floor. Around them, the bones of fish, birds, and mammals that people hunted and processed. Layers that tie human activity directly to a shoreline that is now far offshore. Over the next decades, new tools may make these kinds of discoveries less rare. Higher resolution multi-beam sonar can map the seafloor in exquisite detail. Synthetic aperture sonar can tease out subtle patterns from greater depths. Machine learning systems can sift through terabytes of acoustic data, flagging shapes and textures that resemble known archaeological features, so that human researchers don't have to scan every pixel by eye. Cheap autonomous vehicles, gliding drones and small robotic boats, can crisscross shelves that are currently too expensive to map in detail. At the same time, there is a shift toward broader collaboration. Regional projects that tie together geologists, archaeologists, local fishers, indigenous communities and national agencies, shared databases of cores and seismic lines, agreements that let research vessels move more freely across borders. All of these make it more likely that when a drowned valley does hold something precious, someone will eventually notice. Underneath the maps and models, though, is a quieter story. Whatever else we find out there, most of it will come back to small groups of people watching their familiar world rearrange itself. Families who saw the sandbar where they gathered shellfish become a tidal island, then a set of dangerous shoals, then a patch of open water with no memory on the surface that it had ever been different. Hunters who shifted their camps a little farther inland each generation, passing along stories of the old shore that their grandchildren had never seen. Children who grew up thinking of a wide estuary as normal, never knowing that only a few centuries earlier it had been a flat, grassy plain with reindeer trails and berry patches. They adapted. They moved. They wove the rising water into their myths and navigation and ritual, then into silence, as the details faded and only the broad outlines remained. When we look at the seafloor maps now and try to drape those human lives over the contours, we have to remember how faint the traces can be. A scatter of shells a few centimetres thick, a dark streak in a core where a hearth once burned, a cluster of stones whose only pattern is that they are not quite random. That may be all we ever see of entire coastal traditions that lasted thousands of years. And so the last, quiet question hangs over this whole subject. If we could drain the oceans for a day, just long enough to walk the old shorelines, past the drowned forests and the river mouths, along the terraces where people sat and watched the Ice Age sun set over a very different horizon, how different would our prehistory look? How many of the things we called beginnings would turn out, under that vanished sky, to be continuations of stories that started long before, on coasts we can no longer see? Maybe that is the right place to leave it, on a shoreline we can't quite reach, knowing it's there even if we never set foot on it. In this series, we've traced the edges of that absence. We've followed sea level as it crept and lurched upward after the last glacial maximum, swallowing plains 120 metres below today's tides. We've walked, in imagination, across Doggerland between Britain and Europe, over the wide shelf of Sunda connecting Southeast Asia, along the now drowned margins of Beringia, Sahul, the Persian Gulf, the Indian Shelf, the Mediterranean basins. Everywhere, the pattern repeats. Where we can see into those landscapes through cores, sonar, stray finds dragged up in fishing nets, we glimpse familiar things: hearths, tools, tracks, middens, carved bone, the quiet infrastructure of people making a living along the water, enough to know that rich coastal worlds existed, not enough to stitch them back together in detail, and that is the tension we live with. It's entirely reasonable to feel that the archaeological record is lopsided, that we're mostly seeing the inland survivors of a story that played out first, and perhaps most intensely, along the coasts. It's also reasonable to be wary of leaping from "we are missing a lot" to "there must have been a lost global civilization with technology far beyond what we can document." Mysteries do not need extravagant answers to be profound. A small estuary community whose name we will never know, whose camps are now a faint shadow in seafloor sediments, is no less real for being ordinary. A fish weir under 10 metres of water, a peat-filled hollow where someone once napped stone beside a tidal creek. These are the kinds of secrets the post-Ice Age seas are most likely to have taken. They are enough. As new surveys map more of the continental shelves, as we refine the timelines and fill in a few more blanks, there will still be things we can't recover. Whole mythologies drowned with the coasts, languages that never left a mark on clay or bone, routes of migration we can only infer from a hint of DNA, a scatter of tools, a submerged river mouth. Prehistory will probably always have that soft, blurry horizon at the water's edge. If you've stayed with this episode all the way to that horizon, you're part of a small, quiet group who finds comfort in slow questions and unfinished stories. If you'd like to help more people drift off with this kind of deep time thinking, you can gently tap like or subscribe so you don't miss future journeys along these lost coasts. If you feel like it, you can also leave a comment telling me where in the world you're listening from. Modern shore, inland city, mountain valley. It's a nice way to remember how many different landscapes are sharing the same night. And if this blend of evidence-first history and half-hidden worlds speaks to you, I've written a book that goes deeper into these prehistoric secrets, the bottlenecks, the drowned plains, the quiet revolutions that shaped us long before writing. You can read more about it, or pick up a copy at sleepytimehistory.com. For now, just let the idea settle that somewhere out beyond the present coastline, under a few dozen metres of dark water, the old shorelines still lie exactly where people once walked. Their fires have gone out, their stories have faded, but the shape of their world is still there, waiting in the silt and sand. Let your mind drift there if you like, or let it go entirely. Either way, sleep well, and I'll see you next time at the edge of another forgotten world.